Okay, so hello everyone. Just a second. So I'll wait for 1-2 minutes. Okay, so hello everyone. I'm Kaustav Mukherjee from ISER Bhopal as a TA for this course on Advanced Quantum Mechanics and Application, and today is the last day of the tutorial, that is the week 8th. So today we are mostly going to take on some questions on time-dependent perturbation theory. We are going to take up some problems. We are going to solve multi-level system, time-dependent perturbation theory with multi-level systems, and towards the end of this session we are going to have a recap of the quantum mechanics that both quantum mechanics and quantum information theory that we have been through this tutorial, through these 8 weeks of tutorial, as well as from the lectures as well. Okay, so following from the theme of this week's lectures, so we are mainly going to consider so most of the time, like in the lectures or in the books, you have seen the time dependent perturbation theory for two level system, right? That is, if you have 0 and 1. And today we are going to take up for the case of multi-level system. So it's like we are going to generalize to a n level system. So let's say there are n levels, and let us look at some of the perturbative functions and how they behave for such a system where we have n levels. Okay, so first of all we have our Hamiltonian in the form of the perturbative. This one is the perturbative part, and H naught is the non-perturbative part, right? And this H prime depends on t, it's a function of t. Okay, and what we have, so what we already know, let's just write the givens. So H naught psi n, so psi n is the wave function for all the n states, is given as En psi n. Okay, and we have the orthonormality valid for the wave functions. Okay, and your general wave function psi can be written in the form of Cn of psi n. Okay, so this is the general wave function for n equal to 1 to n. So this is an n level system, right? So from the lectures or from the textbooks, you must have already seen that for a 2-level system you have something, the time dependent perturbation theory gives you something of this sort: minus I Ea t by h bar plus Cb of t Ib t of h bar, where we have two levels having energy Ea and Eb, right? So this is the general wave function for a 2-level system, but for n levels this gets a bit more complex, right? So what we have is so the wave function can be similarly written in the form n Cn of t minus I e to the power n t by h bar, right? So this is your this is your general wave function for a n level system. Now we have our time dependent Schrodinger equation. So next we have our time dependent Schrodinger equation, which gives us your I h bar del psi by del t equal to h psi. So let us first take on the right hand side, that is the h psi. So we know h is written in the form of h naught plus h prime, where h prime is a function of t, and let us say that h prime is active after t equal to 0. So before t equal to 0 there was no perturbation. After t equal to 0 only the h prime is activated, and we have our psi written as Cn of t e to the power minus I t by h bar psi n. Okay, now we know h naught is a eigen, so we know En is the eigenstate for the h naught for psi n state, which we have mentioned over here at the top. So we can write this as Cn of t En. So h naught acting on psi n gives us En psi n. So we have substituted this here, and rest we have t by h bar psi n, plus we have our h prime as it is. So let's now take out the function. Let's just keep it something like this. And on the left hand side we had I h bar del psi by del t. So let's just write down del psi by del t first, and then we can multiply by I h bar. So this is as Cn of t e to the power minus t by h bar psi n, right? So first we take the derivative of Cn, and then we take the derivative of the exponential. There are only two functions with the t here, right? So what we get is summation Cn dot psi n minus I by h bar, and since En is a function of n, so we have to take it in the summation. So what we get is En Cn of t and the exponential with psi n. Okay, now once you multiply your I h bar onto this del psi by del t, you essentially get I h bar summation over n Cn dot t by h bar, and then we have I square, which gives us a minus sign, and we already have a minus sign, and h bar gets cancelled out, so we are left with only plus n Cn of t En e to the power minus En t by h bar psi n. Okay, now if you carefully look at these term and this term, they are identical. So on either side of the equal to, we have these term as common, so these gets cancelled out, and what remains essentially is the other term that we have. Okay, so I'll just take it. Right, and on the other side we have our I h bar summation over n Cn dot, we have psi n here, Ent by h bar psi of. Now once you multiply with bra of psi m, so let's say you multiply with psi m, okay, so let's take it inside the summation, and the rest remains as it is. And similarly for the other side, we have summation over n Cn dot t e to the power t by h bar psi m psi n, and we know this is a delta function because of the orthonormality that it has to follow, right? Okay, yes. So what we essentially end up, so you can write this part as your HMN. So what you essentially get here is summation over n HMN Cn of t e to the power IENT by h bar. Now on other side the summation over n goes off because the delta function, so it becomes m everywhere, e to the power minus I e m t by h bar. So now once you write your Cm dot, you can write it as minus I by h bar summation over n h mn Cn of t e to the power I em minus en t by h bar. So this is a generalized time dependent coefficient for n level system. Okay, now once you have this, you can next consider other cases. So let's say we initialize the system such that only the nth state is populated initially. So what does that mean is that psi n of 0 is equals to 1 and psi m of 0 equals to 0 for m not equal to n. Okay, so there's, I missed the prime almost everywhere. Yeah, that is right. Okay, so now what we have to do is, so till now we have only derived the coefficient, the time dependent coefficient, using the time dependent perturbation theory, and now we are going to take on some perturbative functions and see how our probability of the transition probability comes out to be for transition from m to n states or n to m states. Okay, so let's say we are considering the nth state to be initially populated and all other state to be 0. Okay, so now using this time dependent perturbation theory, what we have to find out is your transition probability. So for that we first need to find the Cm and Cn, right? So your Cn dot, okay, now here you can see that only the psi n, okay, so in this summation, this is sum over m, no, this is sum over n, okay, and we have the psi n. Okay, so your Cn dot is essentially written as, so you can say sorry, this should be C, not psi. So okay, so your Cn of 0 is equal to 1 and Cm of 0 is equal to 0 for m not equal to n. So here only the nth term, so for n equal to n only this expression survives and otherwise it won't, right? So Cn dot of t can be written as minus I h bar h n n prime, and Cn of 0 is essentially your 1, and what we have here is I en minus en t by h bar. So this is also 0, so you get only minus I by h bar h prime and n. So this is your Cn dot of t, right? So you can calculate you can calculate easily that your Cn of t will be nothing but 1 minus I h bar 0 to t h prime n t prime dt prime. So this is the initial, your 0th order, and then this comes from the first order of the time dependent perturbation theory. Okay, so you have found the expression for Cn of t. Now for m not equal to n, your Cm dot is essentially written as minus I by h bar. So from the summation only the n term remains, because initially all other Cm are 0. So we so only for n equal to m n this remains, right? So what we get is Cn of t h prime m n e to the power I e m minus e n t by h bar. Okay, and this part is essentially 1 for the 0th order. So what we end up getting is Cm of t as minus I h bar 0 to t m n prime, this is t prime I n t by h bar, this is also t prime, and dt prime. Okay, from 0 to t prime. So these are the two coefficients that we get. So for m not equal to n, we have this expression, and for n we have this expression, right? Now once we have this, let us consider some examples where we can implement this and find out the transition probabilities for some cases. So mainly we are going to take two problems. First one is a constant h prime from 0 to t naught. Okay, so that means we have a function something like this. This is your t and this is your h prime, and h prime goes something like this, and this is your t naught. So from 0 to t naught you have a constant value, and otherwise it's non-zero. And second problem that we are going to consider is h prime equal to v cos omega t, which is nothing but a sinusoidal function. Sorry. So this is still negative, and we have something like this, right, with frequency omega. So we are going to take on these two problems here. So let's consider first the constant h prime. Okay, now when it's constant you can actually take it out of the integration, and we only are left with the exponential part to integrate over. Okay, so let's do that. So let's first do for Cm of t. So we have this expression here, we can copy paste. Okay, and everywhere we just replace the m small m's with the capital M's. Okay, so this is a capital M that we are looking for. So we are going to check the probability of transition from n to m. So as I said, the n state is initially populated, and we are going to look for the probability of transition to the m state, capital M state. Okay, now here you can essentially take out your h prime. Let's just keep it. So this is just independent of function, and the integration goes from 0 to t naught, because the function only is valid till t naught, and after that it's 0. Okay, so what we get here is your em minus en t prime by h bar dt prime, and this integration is straightforward. You get m minus en t prime by h bar over minus en h bar, and this from 0 to t naught. Okay, so now what we end up getting, this gets cancelled out, so we are left with mn em minus en, and here we have em minus en t naught by h bar minus 1. And now in order to simplify it, what we can do is we can take the half factor with the exponential out, and we can write it in the form of sinusoidal sine. So we get em minus en t naught by 2 h bar, and this bracket comes out to be sine em minus en t naught by h bar. Okay, so this is straightforward. You just take out the half and you get e to the power x minus e to the power minus x, and you just multiply it by 2i in the numerator and denominator, and you end up getting a sine function. Now the probability of transition from n to m is nothing but your mod square of the cm square. So what we have just found out. So this essentially comes out to be mn square by em minus en whole square, and we have a 4 factor coming from the 2 square, and sine square of em minus en t naught by h bar. Okay, now one interesting thing you might find out is that when you try to look at the normalization, so we know that our wave function is our wave functions are always normalized, right? Now it should be the case whether your Hamiltonian is time dependent or independent of time. Okay, so let us look at the normalization factor here, or just a sum over this. Okay, so what we have here is that m equal to 1 to n cm mod square. You can break it out as cn mod square plus summation over m not equal to n cm mod square. Okay, so for that we should calculate the cn as well. Okay, let me just quickly do that. So what we have found out from here is that cn is 1 minus I by h bar integral of h prime and t prime. So your h prime is independent of time, so it comes out and you only get a t factor. Okay, so this is straightforward. This is like nothing but your 1 minus I by h bar h prime nn t naught. Okay, since the integral goes from 0 to t naught. Okay, so now when you take the mod square of that, you get 1 plus h prime nn square t naught square by h bar square, and we have a sum over m. You can just replace the capital M with small m and write it as it is. square, and you have sine square term with em minus en. Sorry, it's getting congested here. Just write it below. Sine square em minus en t naught by h bar. Okay, now if you look at carefully, that this can never be, this part can never be less than 0. It's always greater than 0. So what we are essentially getting here is that the sum over the normalization, no matter what you take, is coming out to be greater than 1, which cannot be the case. So in quantum mechanics, it has to be normalized to 1 always. Now this is a discrepancy with our basic fundamental principle of the quantum mechanics. But here we are forgetting one thing, that these coefficients that we are deriving from the time dependent perturbation theory is only valid to the first order of your h prime. Okay, so that means wherever we are getting the h prime square, these terms we have to ignore for the case of normalization. So this is some approximation that we have to consider. And if there are only h prime, right, let's say there are only h prime nm or something, okay, there is no mod square, and it's still in plus, so there, let's say it is positive, then what you have to do is, since this is a function of time, you have to actually at every time step you have to renormalize the function and redo the calculation at every time step all the time. Okay, so that makes it a lot more complex. So this is normally the case, like we get h prime mod square and not h prime, but if one gets h prime, then it can get complex. The thing, okay, it is stuck. Just a second. Okay. Right. Okay, it's back. So yeah, that was the ultimate thing that I wanted to say, the message, take home message. Okay, now let's consider the second problem, second case, that is we have a perturbing term as a function of as a sinusoidal function. Okay, so we can write your h prime mn as vmn cos omega t. Okay, so let us take the same path that we have taken so far. Okay, you can just copy paste from here. Okay, right, so again just replacing the small m's with the capital M's, since we are looking for the capital M transition to n, from n to n. Okay, now let's say this part is constant. Okay, this does not depend on time, so we can take it out of the integral. Vmn, and the only part that remains inside is your cos omega t. Now we can open this term as e to the power I omega t plus e to the power minus I omega t by 2. Okay, so let's do that. H bar v m n by 2. So I'll straightforward multiply the terms as well. So what we have here is, so there is a denominator h bar, so we multiplied that h bar to omega and n minus e n t prime by h bar. So this is the first term, and the second term is also similar, so let's just write dt prime here. Second term is your e minus h bar omega plus em minus en t prime by h bar dt prime. Now there are two cases that we have to consider here. Okay, so there is a possibility that em is greater than en. So it's like you have these levels and your em is higher than en. So your transition is from lower to a higher state, let's say from a ground state to a first excited state. And the other case can be your en, or let's say your em is smaller than en. Okay, and in this case essentially your later state is lower than, so you are actually de-exciting the system from a higher state to a lower state. Okay, so let us just do for the first case. Okay, so when we have the first case of em greater than en, basically your em minus en is greater than 0, right? Now here if you have a term like this en, now since this is greater than 0 and this is also greater than 0, so this complete term in the square bracket is much larger than 0, let's say. Okay, now and your other term has minus I h bar omega em minus en, where this term is 0, greater than 0, and this term is negative, of course. So the resonance, the term of the resonance frequency actually comes up from here. So whenever these exponential have the factor which is close to 0, only then they are, let's say, valid, otherwise they are actually 0. So why that is 0 is because of something called rotating wave approximation, that I believe we have discussed in some previous tutorial as well. So what does rotating wave approximation mean is that you have, let's say, a function e to the power I phi of t. Okay, now drawing that, so this is, let's say, your real plane, real axis, and this is imaginary axis. So this is a complex plane. When t is equal to 0, so this is essentially 1. Okay, there is nothing, and then as the t goes on, this starts rotating. Okay, now if phi is very greater than 0, then your average of this rotation comes out to be at the center, which is 0. So this essentially becomes a 0. Okay, whenever phi is much greater than 0, and whenever phi is closer to 0, only those terms we need to consider. So this is what we call as a rotating wave approximation. So because of the very high rotating, so this vector, let's say, is rotating, and because of the very high frequency of rotation, it averages out to 0. Okay, so what we have to say is that the ultimate message is that your em, let's say your h bar omega, is closer to em minus en, and this is also what we call as your resonance frequency. So whenever your frequency is close to the difference between the two states, the energy difference between the two states, only then the system is excited, or otherwise it's not really excited. Okay, so only these transitions take place. Second stuck. Okay, so ultimately what the message is that this term is 0 for EM greater than EN. Okay, and what we are left off with is only the second term. So let me just okay, and this term goes off, and only this part remains without this. Okay, and this is easier to then integrate. So what we have is basically minus I h bar, or let's just write in the form EM minus EN minus h bar omega t prime by h bar by EM minus EN minus h bar omega. There is no minus I by h bar, and these cancels out, so and these goes from 0 to t. Okay, and again you can take half of the exponential out and you end up getting a similar form, mn 2 em minus en by minus h bar omega. Okay, and you take out half to h bar, and you essentially are left with sine of em minus en minus h bar omega t by 2h bar. Okay, and these 2 also gets cancelled out. So ultimately your transition probability for n to m. Okay, so sorry, so there was also one more case, right? So when for em less than en, your second term, so your first term remains and second term goes to 0. Okay, because then your em minus en is also negative, minus h bar omega is also negative, so again it's a very fast rotating function, and that goes to 0, and only the first term remains. So in that case you get a plus h bar omega instead of a minus here. So here you have minus, this becomes plus h bar omega for the em less than en. So your generalized Cm of t can be written as minus Vmn em minus en plus minus h bar omega. Okay, let's e to the power I em minus en plus minus h bar omega t by 2 h bar, and we have I here sine em minus en plus minus h bar omega t by 2 h bar. Okay, so this is your Cm, and now you can directly calculate your transition probability for n to m, which is given by mod Cm of t square, and this is written as Vmn mod square Em minus En square, and you have a sine square. Okay, now if you again do the normalization, okay, and you can see that this transition actually depends on the sign, right? So when you have a sinusoidal function as a perturbation, these actually couple the two states and then they start populating sinusoidally. Okay, now so what you will actually see is something like this. So we have also discussed this earlier. Let's say when you have only two levels, so what will happen, your first level, let's say, which we are considering as n, oscillates like this, and your m oscillates like this. So let's say your laser frequency is only coupling the n and m, then you have something like this. So this is your m and this is your n, okay, and they start oscillating. So these are sine square, so that's why it cannot go negative. Okay, these are populations. So this is the transition probability. Okay, and when you take again your summation over m mod Cm square, you will again find the same thing, that it will come out to be greater than 1 because of the presence of the second order terms. Okay, and this you again have to ignore in order to keep it valid, because the time dependent perturbation theory, we have these coefficients to be valid only till the first order of the perturbation. Okay, so this was the questions that we wish to consider, and next we are okay, just a second, and I have planned on some revision. So we were told to have a quick revision since this is the last week and you have your exams, I suppose, this Sunday. So let me do a quick recap of whatever we have done in this course, whatever you have learned in this course. Okay, so I have broadly divided the recap in as a section of 3. So there is, the first part was on basic quantum mechanics, where we learned about the Schrodinger equation, the coherent states, the angular momentum operator and spin operators. And the second section deals with the quantum information theory, where we essentially learned about quantum entanglement, how one transports, how one teleports a qubit from one place to other place, what are these quantum gates. Okay, and in the third part we have essentially looked at the approximation method. So you can find this, so I've made a notes on this, and I will upload these notes separately for a quick revision. Okay, so you can just go through all the formulas that I have kept in short, just for a quick recap before your exam. Okay, so for in the section 1 we essentially dealt with Schrodinger equation, where we had two forms. There was time independent Schrodinger equation and a time dependent Schrodinger equation. So the time independent Schrodinger equation essentially dealt with the spatial form, so you had infinite potential, harmonic oscillator and everything. And in the time dependent, you essentially had calculated how it was mainly used right now in the time dependent perturbation theory as well. So you find out the time evolution of the wave function using the time dependent Schrodinger equation. Then we had calculated a lot of wave functions and energies for mostly these typical three systems that are infinite potential or step potential wells. We had a harmonic oscillator and hydrogen atom. Okay, and so these were the wave function that we had obtained for infinite potential with these energy eigenvalues. Similarly, I have only written the ground state for harmonic oscillator and the hydrogen atom. So the other higher excited state you don't really have to memorize, but these you have to keep in mind that the ground state of a harmonic oscillator is a Gaussian wave function. Okay, it also comes handy for variational principle applications and in other areas as well. So you have to keep in mind that the ground state of the harmonic oscillator is a Gaussian wave function, which is also a coherent state that you have already seen. And this is a very simple formula that comes handy almost everywhere, whether it's your exams or competitive exams as well. And similarly, the ground state of hydrogen atom is essential. Rest you need to know the special functions that are used for these wave function, but you don't need to memorize any of that sort. They are mostly given in exams if they are being used. So in case of harmonic oscillator, you have Hermite potential, Hermite polynomials. And in case of hydrogen atom, you have spherical Bessel function for the angular and log Urey. Okay, maybe I'm confused a bit. So you just have these Bessel and log Urey functions to be used as YLM and Rn, I think, yes. And then you have these energy values for the hydrogen, energy levels for hydrogen atom. So this is basically this is what we have learned through your high school as well. So we have minus 13.6 by n square. And then this is one of the most important equation, I feel, the Heisenberg equation of motion. So if you have any operator and you need to find the time evolution of that operator, this is the equation to go for. Okay, so this is one of the most important equation in quantum mechanics that I feel. Next up, we had harmonic oscillator that you had solved using algebraic method as well as proper Schrodinger equation, solving the time dependent, the double derivative, the spatial dependent Schrodinger equation. So there in the algebraic method, you had your lowering operator and raising operator with these eigenvalues. So these are easy to remember and comes handy as well. And you had your position operators defined in this form. So you have to just keep in mind that position operator is a plus a dagger, and momentum operator you have a minus a dagger, and from there on you can find out x and p as a function of a dagger and everything. Okay, whatever you need. And this is also one of the key formula in the whole of quantum mechanics, I feel. So xp commutation is IH bar. This is irrespective of harmonic oscillator. I just kept in the section of harmonic oscillator because it was used mostly in this scenario, but this is valid irrespective of harmonic oscillator. So this is very important commutation relation. And in the case of harmonic oscillator, of course, you have a dagger equal to 1, which you are supposed to, this is easy to keep in mind. Then we had coherent state. The coherent state is essentially derived from the eigenstate of the lowering operator. So one cannot really find the eigenstate of raising operator, but through the eigenstate of lowering operator you find you get a coherent state, which is what we essentially refer to as the most classical part in quantum mechanics. Okay, so it gives us the analogy of the simple pendulum as well, simple harmonic oscillator. Okay, and this was also the key reason of having a eigenstate of lowering operator, because you can't have bounds on the raising operator, but on lowering operator you have a lower bound. Okay, and this was the function of coherent state, where you can see that this essentially represents a Gaussian wave function. And this is also the as I said just now, that this is also the ground state of a harmonic oscillator. Okay, and these are the harmonic oscillators basis. Then we had angular and spin quantum number, and you have already seen how they are very much resembling. So all the commutation relation that we have in angular quantum numbers are exactly looks the same in the quantum spin quantum numbers as well. So these are some of the key commutation relations that I feel are important. Otherwise, others are easy to remember or derived from these key relations. So for example, if you need to find Ly Lz commutation, you know it will be IH bar Lx, and when it's opposite, it's just minus IH bar Lx. Okay, so these are easy to remember, and this is one of the key the eigenvalue of L plus and L minus, which was very important. Okay, and you don't really need to keep this in your memory, but it might come handy if somewhere it's not really given, but it's mostly given in questions. Okay, but it's easy to keep in mind. So these are also same for the spin quantum number. Now coming to section 2, we had we first familiarized ourselves with quantum entanglement. What is quantum entanglement? So any state which can, so let's say you have two Hilbert spaces HA and HP, and a state, if it can be written in the form of tensor products of A and B, then we say it's not entangled. And let's say for example, we can't really write in a general notation for entanglement state. So let's say you have a state of 2 qubits and you have 0 0 and 1 1. So you can see, I'm missing a bracket here. Okay, you can see that you can't really separate them out. Okay, so I can write shortly here. So these are 0 cross 0, 1 cross 1 tensor product 1. So you can't really write in the form of 0 plus 1 tensor product with either 0 or 1. This is like impossible to write in that form, and hence we say that it's a entangled state. So you can't really decouple them, they are going to remain coupled like forever. Okay, then next we had measurement of entropy, which also helps you find out the maximally entangled states in any system. So the measurement of entropy, I don't think so was covered in the lectures. It was there in the tutorials to find the maximally entangled states. So this is essentially something like you take the trace of either the A system or B system, or if you have the combined system, you take something called Shannon entropy, which is very important in quantum information theory. Okay, so if you have this entropy to be 0, then it essentially tells you that the state or system is pure and it's not entangled. And if it comes out to be not equal to 0, then you can confidently say that it's either entangled or mixed state. So it's in case of if you're taking the complete system or only taking some part. Okay, so if you're, let's say, taking only row A, then you can only say if it's mixed or not. And if you're taking the complete system, then you can tell if it's entangled or not. And finally, if you have entropy equal to 1, that refers to it being maximally entangled or maximally mixed state. Okay, then we had a bunch of quantum gates. So first of all, all of these are important actually. So Hadamard gate is essentially used for creating superposition. So let's say if you have a 0 or 1, you can create a superposition of 0 plus 1 or 0 minus 1. Okay, then we have bit flip operator, which is essentially your poly x. So when you operate sigma x on 0, you get a 1, and when you operate on 1, you get a 0. So it just flips the bit from 0 to 1 or 1 to 0. Then we have a phase flip operator, which is non-existent in the classical bits. So in classical bit, you have the bit flip, like you can switch using a NOT gate. If you have a 0, you put a NOT gate, you get a 1. Okay, but this phase flip is only present in the quantum universe. So in phase flip, if you operating on 0, it does nothing, and when you operate it on 1, you get a minus sign, which is essentially introducing e to the power I pi. Okay, then you have a C0 gate, which is very important to create entanglements. Okay, and this is represented in this form. It can be confusing, so keep in mind that this is a solid circle and this is a hollow circle. Solid circle is the controlling bit, and B is the bit in which it acts on. Okay, so if A is 0, then it doesn't do anything. It's like a switch. When you switch on A with 1, it flips the B. Okay, so it's like you're applying C naught on 0 0, does nothing. 0 1, again it does nothing. But when you have A as 1, so 1 0 becomes 1 1, and 1 1 becomes 1 0. So this was a summary of the quantum information part. And finally then we had the approximation methods, in which we initially dealt with time independent perturbation theory, where we have first order correction to the energy and second order correction to the energy. So these formulas come very handy. And then we have our first order correction in the wave function. We don't really have second order correction. That might be a lot more complex. We don't need to take care of that. Then, so these were first three were for non-degenerate case. And then once you have degenerate case, let's say for twofold degeneracy, you can easily keep this in mind. I'm missing a bracket here. Okay. So for two states having same energy, that is psi 1 and psi 2, having giving us the E only, H, let's say H psi 1 is giving you E psi 1 and H psi 2 is also giving you E psi 2, which is a twofold degeneracy, then this is the formula that you need to consider. Then we had variational principle, where the essence was that you take a trial wave function, and whatever wave function you take, unless it's the real ground state wave function, you always get a ground state energy which is greater than your actual ground state energy. So you can take endless number of trial wave function, but you will never get a energy which is lower than the ground state energy. So this sets an upper bound. Okay, so what you essentially had to do is that this was your total Hamiltonian. You had to take the average, and you have a trial wave function which either is given in your question, or you have to consider your own based on. So mostly the systems are in these three forms. You have infinite potential, or some potential, well, harmonic oscillator, or hydrogen atom. So that's why I said that keeping these in your mind will be very helpful for these trial wave functions. So once you have the trial wave function, you can easily calculate the ground state energies. Okay, sorry, I went ahead. So these trial wave function has a variable parameter B through which you have to optimize. So you take the average expectation value of the Hamiltonian with a derivative with respect to dB, and you just put it to 0. You minimize the thing, so you get a ground state energy for that. Okay, then we had WKB approximation, in which this was one of the key equation. So when you have something like double derivative of psi equal to, let's say this can be with respect to x also, or any variable. So if you have double derivative with respect to z, and you have on the right hand side z psi, then you get a wave function in this form which contains ai and bi of z, which are essentially your Aries functions. So these can be useful. You don't really have to memorize the Aries function. You just keep this thing in mind, that if some problem comes where the equation looks like this, then you know the solution is in the is in this form, having Aries function. Next, applying the WKB approximation. When you have a two-sided wall in this form, and you have a potential, slowly varying potential in the middle, then your P of x, so write it in short, this is something which is 2me minus v of x. So this is the v of x is given mostly. Okay, so you have to find out. So these are 0 to a, let's say from some interval to some interval, and you have to find this E out. Okay, and through this formula, set of formulas, you can easily find them out. So you just have to like categorize the problem based on number of walls it has. So let's say if it has two-side wall, like in this case, then you have to use n pi h bar. If you have one-sided wall, then you have n minus 1 by 4 pi h bar, and if there are no walls, so this middle is not actually a wall, sorry, it was actually axis, so I'll just draw it this way. Okay, yeah, and here it is valid only in the middle part. Okay, so there are, like, you can't really calculate, sorry, for this case it was, so you can't really find the and then, like, it does not really work where there are walls, so you have to stay a bit far away from the wall, and you find out your En, right? You can find out your E of n, the n energy levels, based on these three formula set. Okay, so this was okay, I think I missed the time dependent perturbation theory part here. So it was anyway done today, so I'll just give a short recap of today's tutorial as well. This is 4th. So what we had is, like, for 2 level case, let's say, we can write, or for n level also. So let me just find the formulas. Right, so when you have your nth state, so there are n levels, let's say, and you have your nth state to be populated initially. Cn of 0 is 1, Cm of 0 is 0 for m not equal to n. Then we had Cn of t as 1 minus I h bar. Since this is more general, so I am writing in terms of n only. Dt prime, and your Cm of t for m not equal to n was given as minus I h bar 0 to t h prime m n. You can actually derive this on the spot as well. It might take some time, but these are easy to remember as well. It's not very hefty equations. You can just take them. And one more formula that you can keep in mind. So let's say this is first, second, and finally you have your probability of transition from n to m, which is given as Cm of t mod square. So I believe these are all the formulas. Yes, I suppose so. Rest, based on the perturbative function, you have to calculate these coefficients as a function of time or the transition probability that you have to find out. So I suppose this is it. I have enjoyed these tutorials, and I wish you all the best for your exams. So thank you for joining these sessions. Yeah, thank you for joining these sessions. Yeah, I enjoyed this. Yeah. Okay, take care and all the best for your exams.